Let us begin with the derivation of magnetic field intensity due to a conductor carrying current of I amperes. And this conductor can be a finite length of conductor, or it can go for infinitely long conductor. So we are going to do these two in a single derivation, where first we will get the expression for magnetic field intensity due to finite length of conductor, and we can extend it to infinite length. Whenever we have a current carrying conductor, magnetic field will be produced around the current carrying conductor in the form of concentric circles, where the direction of the magnetic field can be given by right hand thumb rule, where if thumb indicate the direction of current, fingers point the direction of magnetic field around the current carrying conductor. In this case, if I is flowing upward or in the positive z direction, our magnetic field lines will be in the direction of phi or angular phi variation. We are going to follow the cylindrical system. And from Biot-Savart law, we can find what is the magnetic field intensity due to a current carrying conductor, where IdL cross R divided by 4 pi R cube has to be integrated over the length of the conductor. Since we are first assuming a finite length of conductor, the integration will be with respect to the length variable, that is z variable, where the lowest limit of z is z1 to the highest limit is z2. That is, the length of the conductor is extending from z1 to z2. If the current element IDL is taken along the length of this conductor is running in z direction. So dl vector can be written as dz az vector, and IDL current element will be idz az. Next, we need to find what is r vector. So r vector should be found knowing the coordinates of the current element and the point P where we are finding the magnetic field intensity. Let us consider the point P is oriented along y-axis at a distance of rho from the axis of the cylinder, and the angular variation is taken from x-axis along xy plane. So let us consider the angle is phi, and at a height of z0, we are assuming the point P. Now, let us consider the points coordinates for current element IDL. IDL is along the axis of the cylinder, so radius will be 0 along the axis of the cylinder. And if I'm finding the vector r along the plane where the line joining IDL and point P is considered, so the angle of the point P and angle of the current element should be same. So I'm maintaining the same angle phi, which is considered for point P, also here for IDL. Then this IDL is considered at a length or height of z from z equal to 0. So the coordinates of IDL will be 0, phi, z. With the coordinates of IDL and the point P, r vector from IDL to point P can be written accordingly. So therefore, we will get rho minus 0 in arrow direction, phi minus phi in a phi direction, and 0 minus z in az direction. Therefore, our resulting r vector will be rho arrow vector minus z az vector. If I find magnitude of this, that will become under root rho square plus z square. Now we have got IDL vector and r vector both. We have to estimate IDL cross product r vector in the numerator. We have already discussed cross product between two vectors can be found as a determinant rule, where first row will be the components of unit vector. Here in cylindrical system, we have A row, A phi and AZ are the unit vectors. And the second row will be the components of ideal vector. When you look at ideal vector, it has only Z component. So rho and phi are 0 and the Z component is ideal. Then the third row will be for the vector R. Vector R's rho, phi and Z component should be written. R vector has rho component as rho, phi component 0 and Z component minus Z. When you expand this determinant, we will get A rho component becoming 0 and A phi component becoming minus rho idz, where one negative sign is there for this A phi component, and AZ component is becoming 0. So the resulting ideal cross R vector is in the phi direction that has the magnitude I rho dz A phi. So this is ideal cross R. We can substitute this ideal cross R into DH vector and integrate it over the entire length of the conductor will give magnetic field intensity produced by finite length of the conductor. So instead of ideal cross R, we are putting I rho dz a phi, and the integration variable is z variable. Z has to be integrated throughout the length of the finite conductor, that is from z1 to z2. So the lower limit is z1 and upper limit is z2. And when you look at this expression, which is integration with respect to z, it is a little complicated to evaluate. So we are going for substitution method. We will replace, instead of rho square plus z square, some variable, or instead of z, we are transforming it into some angular variable alpha. If we consider a right angle triangle, including this line joining ideal and point P and z-axis and y-axis, this relation we can get between z and angle, included angle alpha. So the height z is from the origin to the current element ideal, and point P is at a distance of rho from axis. So this is rho, and the included angle is alpha. In this right angle triangle, the opposite side becomes z variable and adjacent side becomes rho variable, where hypotenuse is magnitude of r vector. So the relation between z and angle alpha can be written as z can be written as rho tan alpha, where tan alpha indicates opposite side by adjacent side, where this opposite side z can be written as rho into tan of alpha. Now, instead of z variable, we have to replace in terms of alpha variable. Instead of dz, we should write the substitution by differentiating this expression. If you differentiate this expression, we will get dz in the left-hand side. In the right-hand side, rho is constant. Only thing is when z varies, alpha varies. So the point P coordinates are fixed. So rho value is going to be constant. Differentiation of tan alpha will be 6 square alpha d alpha. So wherever we have dz, we have to replace rho secant square alpha d alpha. Now we should consider changing limits from z to alpha. Again, looking at this diagram, the lower limit of z is z1 and the corresponding angle will be alpha 1. The upper limit of z is z2 and the corresponding angle will be alpha 2. So when we change the variable z to alpha, the limits will be changed to alpha 1 as the lower limit and alpha 2 as the upper limit. Substituting that in the expression for h, instead of dz, we can write rho secant square alpha d alpha, and instead of z, we can write rho tan alpha, and changing the limits to alpha 1 and alpha 2. By substitution, and we can do integration for alpha variable. The denominator expression can be simplified, taking rho square common outside, and rho square, the whole power 3 by 2 will become rho cube in the denominator. There is rho square in the numerator, and rho cube in the denominator will give 1 by rho in the denominator, or 1 by rho term. And this I by 4 pi rho is constant. We can take outside the integration. The integration variable is alpha, so alpha terms will be kept inside. Here we have 1 plus tan square alpha in the denominator. So 1 plus tan square alpha will become 6 square alpha. 6 square alpha, the whole power 3 by 2 in the denominator will give 6 cube alpha in the denominator. Numerator has 6 square alpha. So you'll get 1 by 6 alpha d alpha for the integration. Now integration will be with respect to alpha. 1 by 6 can be written as cos, and integration of cos is sine. Applying the limits, lower limit is alpha 1 and upper limit is alpha 2. We get the expression for h due to finite length of conductor, that is I by 4 pi rho sine alpha 2 minus sine alpha 1 a phi cap. Then we can extend this length to infinitely long conductor. Thereby, we will get the expression for magnetic field intensity due to infinitely long conductor. The upper limit z2 will reach positive infinity and lower limit z1 will reach negative infinity. And similarly, we can transform to alpha variable again. From the expression, we can write alpha as tan inverse z by rho. If z is minus infinity, alpha will become minus pi by 2. And if z is plus infinity, alpha will become plus pi by 2. So the limits will be lower limit alpha 1 will become minus pi by 2 and upper limit alpha 2 will become pi by 2. So in this expression for finite length of conductor, we can change alpha 2 to plus pi by 2. So sine of plus pi by 2 will be plus 1 and alpha 2 will be minus pi by 2. So minus of sine minus pi by 2 will be again plus 1. So 1 plus 1 will be 2 in the numerator. That will be cancelled with 4 in the denominator. Thereby, we are getting I by 2 pi rho A phi vector. This is the expression for magnetic field due to infinitely long conductor.